So because this video might end up being quite long, because we're going to cover quite a lot of things, I'm going to start with just a quick breakdown of what exactly we will be covering. The first thing I'm going to do is just give a quick summary of what exactly Kerberos is, because maybe you've never heard of it, maybe you don't know what this whole video is about. So it'll just be a brief description of what the purpose of Kerberos is. And the way I've decided to do things after that is that we're going to go through the same process multiple times, but in a lot more detail each time, essentially. So we'll start with the process of how a user logs on, and then how they request access to a service, and then how they actually access that service. So that's the kind of overall process that we're going to go through multiple times. We'll start off with a very simple summary of that so you can just get a general idea for it. Then we'll go through it again in a bit more detail, covering some technical details, some of the nuances, and some of the small things that are important but that are kind of left out in a high-level summary. And then finally, we'll look at it again, but this time looking at the actual messages that get sent across the network, the format of them, the kind of information they contain, and how everything actually goes together. As part of that, you'll see exactly how service principal names, or SPNs, come into all of this. I'll also highlight the things that actually allow silver ticket and golden ticket attacks to happen. And then to kind of sum everything up, we're going to take a look at a live demo of an application actually authenticating with Kerberos, and we'll look at the Wireshark network trace and actually see where all of this stuff that we've talked about actually fits in the real world and how it actually looks. So hopefully after all of that, you'll have a good understanding of how Kerberos works, and also a good understanding of exactly how and why certain attacks work against it. Speaking of which, if you're new to the channel, there will be a link in the description to a playlist that contains all of my previous Kerberos attack demonstration and explanation videos. So take a look at those if you're curious how those attacks actually work in the real world. So with all of that said, let's get started with a very basic explanation of what Kerberos is and what its purpose is. It is essentially an authentication protocol. And what that means is that it's a way to prove that a user is who they say they are across the network. So if you've got a program running on one computer over here, and it wants to talk to this service over here across the network, and let's say that service only allows certain user accounts to access it, or it at least contains some items in it that it only wants certain users to access. If you think of like an SQL database, which is the example we're going to use throughout this whole video, there might be some databases that one user account is allowed to access, and then some other databases that other user accounts are allowed to access, and that first user account is not allowed to access. So we need some way of proving that a user is authentic, hence the name authentication, proving that they're authentic in that they are who they say they are. If we didn't have something like this, then, well, any user can just send us a request saying, yeah, I'm the domain admin, let me access everything. Obviously, we don't want that. So we need some way to prove that a user actually is the domain admin, or is whoever else they say they are. Of course, this is a very common situation, so there's plenty of other protocols that do this kind of thing. One of them that's very common in Windows networks is NTLM. You've probably heard of that. And even though Kerberos is supposed to be the kind of default authentication mechanism used in Active Directory domains, there's still quite a lot of situations where NTLM will get used instead. One example being if you connect to something via its IP address instead of its host name, that will not use Kerberos, that will fall back to NTLM authentication. So as you probably guessed by the way I'm saying it will fall back to NTLM, Kerberos is generally considered to be much more secure than NTLM. As you'll see throughout this video though, that doesn't mean that it can't be attacked or it's not vulnerable in certain ways, but on the whole, it's generally considered to be much better than NTLM. So how does Kerberos actually work then? Let's look at this first run through of the whole process of a user logging on and then accessing a service. We've got our user account over here called John Smith. His username is just j.smith. When he logs on to this computer, he's going to talk to a domain controller, and that's one thing to point out straight away actually, is that even though this is Kerberos in general that we're talking about, I'm only going to be explaining how it works in an Active Directory environment, because to me that's what's most useful. Like, it's okay talking about the Kerberos spec in general, but 99% of the time when you're dealing with Kerberos, it's going to be in a Windows network with an Active Directory domain. So that's all I'm going to be focusing on here. And Microsoft did make some changes to the Kerberos spec when they implemented it. Their implementation is called MS-Kile, K-I-L-E. I'll leave a link to the documentation for that in the description. For the most part though, it does very closely follow the Kerberos specification. So yeah, coming back to the process of logging on. We've got our user, JSmith. He communicates with a domain controller and he says, I would like a ticket for JSmith. The domain controller sends him back a ticket for that user account. Again, don't worry if you don't understand what a ticket is at this point. We're going to go into that in a lot more detail. This is just a high-level overview. So the domain controller sends him back a ticket, and generally the Windows machine that he's on will cache that ticket for the duration of his logon session. So that ticket, his initial user ticket, or a TGT as it's sometimes called, that ticket will stay on his machine, and he doesn't have to repeat these first two steps again until either he logs off or until the ticket expires, but we'll get into that later. So once he's got this initial ticket, you can then use that to request access to a service. And again, here we're using SQL Server as a good example because it's a fairly common thing that everybody knows about, and it supports Kerberos Authentication. So obviously, bear in mind going through all of these examples, we're going to be using SQL, but you could swap that out for any service that allows a user to authenticate via Kerberos. So the user wants to access the SQL service on a certain server. It sends a request to the domain controller asking for a ticket for that service. And as part of that request, to prove that the user is who they say they are, they supply the original ticket that they got as part of their logon process. So they take that user ticket, they send that to the domain controller and say, I would like to use this ticket to ask for a ticket for the SQL service. It gets a little bit confusing, but don't worry, they are the only two tickets in this whole process. The domain controller doesn't actually do any kind of check at this point to see if the user is allowed to do that. It will just send back a service ticket for the SQL service, regardless of whether the user is actually allowed to access the SQL service. So any user can request a service ticket for any service. And in the next step, you'll see why, in theory, that doesn't matter. It's not a security risk. In reality, it can be, but we'll get to that later on. So the user's now got their original user ticket, which they've just kept in their cache and they could use to request more service tickets. But they've also now got this service ticket for the SQL service that the domain controller has sent back to them. Now what they can do is actually initiate a connection to the SQL server. So this is the first time they actually communicate with the server and the service that they're trying to access. So it sends that ticket to the SQL service as part of the initial authentication request. And the ticket proves that the user is J. Smith. And it also includes a list of the groups that they're a member of and other information about the user account. And because of the way this whole process works, the SQL server doesn't, in theory, need to contact the domain controller to confirm any of this. It trusts that everything in the ticket is accurate and that the user is J. Smith and that they are a member of these groups that the ticket says they're a member of. Now, obviously, from just looking at the summary there, it doesn't really make any sense why the service would just trust that ticket as being accurate. But as you'll see in a minute when we go through this in more detail, in theory, there's no way that somebody should be able to fake the ticket. So just a real quick recap again. When the user logs on, so these first two steps only happen during the initial logon, we ask for a ticket for J. Smith. The domain controller sends us a ticket for J. Smith. Then when we want to access a service, we ask for a ticket for that service and we supply our user ticket to prove that we are J. Smith. We get back a service ticket for the SQL service, and then we send that ticket to the SQL service, and that proves that we are the user we say we are. So now it's up to the SQL server to decide if it wants to let us in. And that's why, in theory, step 4 isn't a security issue. The domain controller sending out a service ticket for any service to any user, that shouldn't be a security issue, because the point of Kerberos is just to authenticate people. It's just to prove they are who they say they are. It's not to decide if they should be allowed in. That's up to the SQL server to decide that once it knows who they are. So when we get to step 6, where the service ticket has proved that this user is J. Smith, well, now the SQL server can say, actually, J. Smith shouldn't be allowed access to this database and just deny them. So hopefully that makes sense as a very high-level overview. I'm sure you probably got a lot of questions as to how this is all actually secure. So let's take a look at the same process again, but in a bit more detail. And the first thing that we need to explain that's not going to be actually on this diagram is that every Active Directory domain has an account called the KRB TGT account. If we flick over to my example domain controller here, so we've got just a bog standard Active Directory domain. If we go into the users container, you won't see them by default, but if you go to view and then advanced features, and now we go back to that same users container, you see this account here, this KRB TGT account, and it's described as the Key Distribution Center Service account. Now, Key Distribution Center, or KDC as it's commonly shortened to, in Kerberos language, that basically just means the central database that stores the users and passwords and that handles incoming ticket requests. So in Active Directory, that is basically every domain controller. So whenever you see KDC or Key Distribution Center, you can just think that that means domain controller. And even though it is a user account, you can't actually log on with that account. You'll see it's disabled by default. I don't think you can actually enable it either. No, you can't. And it has its password set by the system to something really long, really complicated. You don't ever need to actually know what it is. You won't ever have to log on as that account. You can reset the password, and we'll come to that later on, why that's probably a good idea to do every now and then. But for now, just know that there's this user account in the domain, and that it has a really long, complex password that the system knows, and that nothing else knows. And that's an important point, is that nothing else should ever know this password. So now that we understand that, let's look at this whole process again. So our user requests a ticket for their user account. They don't send their password with that user account. What they do send is some data that was encrypted using their password. This is known as pre-authentication data, and if you've watched my video on Kerberos pre-authentication and how to attack accounts that don't have that enabled, then you'll understand why it's important. For now, we're just going to assume that this account has pre-authentication enabled because that's the default. So because the user account has pre-authentication enabled, we're going to send the current time encrypted with the user's password. The domain controller receives that request, And because the domain controller can read everybody's passwords, it decrypts that timestamp using the user's password, because that's what it was encrypted with. And then it can see if that timestamp is current. So this is a way to help detect replay attacks, basically. But again, not too important for now. Let's just assume that the user did use the correct password. The domain controller checks it, and it's all good. So it sends back the TGT, which is the ticket granting ticket. And it's fairly obvious why it's named that, because it's a ticket that can then be used to request other tickets for other services like SQL, as we saw. And along with that TGT, it also sends a session key. Now this key at first doesn't seem too important, but it's actually kind of the key, no pun intended, for how this whole thing works. That session key is both inside the TGT and also sent separately. And in each case, it's encrypted in a different way. So let's just say the session key was hello. Like, it's not actually text, it'll just be random bytes, but let's just assume that this session key is the word hello. The word hello will get encrypted using the KRB TGT account's password as part of the ticket. So it'll get stored inside the ticket, and the whole ticket is encrypted with the KRB TGT account password, which nobody else knows other than the domain controllers. And alongside the ticket, it also sends that same session key, so the word hello, but encrypted with the user's password. So John Smith's password in this case. So now the user has got this ticket that they can't read because it's encrypted with the KRB TGT account password, and they've got the session key, which they can read once they decrypt it using their password. So if an attacker was to request a ticket for J. Smith and they don't have his password, well, they're going to get back a lot of useless data. They're going to get the TGT that's encrypted with a password they don't have, the KRB TGT account, and they're going to get the session key, which is encrypted with a password they don't have. So they can't perform the next step, which is to send a request to the domain controller for a service ticket, as we saw before, and pass on that user ticket, which nobody can read apart from the domain controller. And they also send what's called an authenticator, which is just some data. There's nothing particularly special in the data. It's just like the user's username, a timestamp, but it's encrypted with the session key. Now remember, the session key is inside the ticket that nobody can read apart from the domain controllers, which we're sending to the domain controller. The only other way to get the session key was to have that user's password. So if we were an attacker, we don't have the user's password, we can't do this whole step, because even if we somehow got hold of a ticket that was sent for that user account, we can't send the authenticator, which is just data encrypted with the session key, because we couldn't decrypt the session key. So we couldn't get that word hello in our example. So let's say we use the wrong password to encrypt this data. We pretend we know the session key as an attacker. We send that with the ticket off to the domain controller. The domain controller is going to decrypt the ticket using its KRB TGT account password. It'll read the session key from inside the ticket, which will, again, in our example, just be the word hello. It then tries to use that session key to decrypt the data that we sent as an authenticator. And obviously that's going to fail because we don't have the session key, because the only way to get the session key was if we had J. Smith's password, and in which case this is all legitimate. So hopefully that makes sense. It's the fact that the session key is in the ticket, which we can't change or fake because it's encrypted with the KRB TGT account's password. The fact that the session key is in there, and that we had to use that same session key to encrypt some data and send that with the request. If those two keys don't match, which they're not going to unless we have the password for J. Smith, because that's how we get the session key in the first place, well then this request is going to fail. The only time it succeeds is if we do have the password for J. Smith. We completed step 2, which gave us the ticket with the session key inside it, and also a copy of the session key encrypted with our password. Then we can pass on the ticket and some more data encrypted with the session key, and everything's fine. I feel like I repeated myself a lot there, but it took me a little while to get my head around, so I'm trying to kind of really drive it home for you guys, but apologies if I made things more confusing there. Hopefully you get the idea. So that brings us on to step 4 and 5, which is pretty much a repeat of step 2 and 3, but with the service ticket instead of with the ticket granting ticket. So the user sent the request to the DC in step 3. Assuming everything checks out, the DC sends back a service ticket for the service that they've requested, SQL in this example, and a new session key. Like I say, this is very similar to the previous steps. The service ticket has a session key inside of it. The service ticket is encrypted with the service account's password, not the KRB TGT account this time, the account that runs that service. How does the domain controller know which account is responsible for which service? That's where service principal names come in, or SPNs or SPINs. There's lots of different ways to pronounce them. But yeah, a service principal name, which let's just take a quick look at now on the domain controller. If we go to our service here, our SQL service user, and we look at their attributes, there's other ways to do this, but this is just a quick, simple way. We look at this attribute called service principal name. You'll see here it's got MS SQL service, and then the name of the machine that the service is running on. There's a few different ways that a service principal name can be constructed, which is why we also have this one with a port number, but you get the idea. It's the service name and then the machine that it's running on. So if we go back to our diagram, in step 4 here, where the domain controller is sending the service ticket back, and it's encrypting that service ticket with the service account's password, basically all it's doing is just searching the domain for the account that has a service principal name that matches the request that the client sent. So when the client sends a request in step 3, it constructs the service principal name, because the client knows it wants to connect to SQL server 1.mydomain.local, and it wants to connect to the MS SQL service, so it can construct that service principal name, send that with the request in step 3. So the domain controller searches the domain, finds the account that's responsible for that service on that machine, uses that account's password to encrypt the ticket. And then same as before, there's a session key inside that ticket, and then there's also a copy of that same session key, but encrypted with the user's password sent along with it. So now we've got the exact same scenario where the user can decrypt the session key with their own password, and then step 5 is very similar to step 3, but instead of sending a ticket to a domain controller and asking for a service ticket back, now we're sending a ticket to the actual service we want to authenticate with, and we're using the exact same method to prove that everything's legitimate. We send them the service ticket, encrypted with the service account's password, and some data that we've encrypted with the session key, which again, we can only get the session key if we actually have the password for J Smith. And remember, the whole purpose of this is to prove that we are J Smith, to prove that we have that user account's password. That's basically what authentication is. It's just proving that you have the password for that account. So in step 6, the SQL service decrypts that ticket that it was sent, the service ticket, because again, it was encrypted using the SQL service account's password. The SQL service is running as that account. If it wasn't, if you'd left the SQL services on this machine running as local system instead of running as this user account in Active Directory that has the SPN associated with it, then this would just fail. But assuming that the SQL service is actually running as that SQL service user account, it can decrypt the ticket because it has access to its own password. And again, it can get the session key from that ticket and then compare that to the session key that was used to encrypt the authenticator that was sent with it. If they match, then we know that this request is legitimate, or at least that it's come from somebody that has the password for this account. And again, that's all we're checking for. Now, when I first looked into this, there was one part that confused me about all of this. Well, the whole thing confused me when I first looked into it, but after spending a bit of time getting my head around it all, in step 6, where we're saying that the SQL service can just decrypt the ticket because it has access to its own password, well, that's not strictly true, because if you write a program, and again, SQL isn't anything special, it's just a program that somebody's written, you can't just read the password from Active Directory or from your own logon session of the user account that you're running as. But it turns out there's a set of Windows APIs such as accept security context and acquire credentials handle, all these things, I'll leave a link to them in the description, that basically take care of this for you. Because the operating system does have access to a hash of the user's password, even if a program that's running doesn't actually directly have access to it. Also, just to point out, when we say credentials and passwords, it's not literally the actual password that a user account has, it'll be an NTLM hash of that password. So there's still no direct way to just get the user's password, that's not stored in plain text anywhere. This will just be a hash of the password, and that's what's used to encrypt these tickets. So now that we know all of this, let's take a look at some of the ways that this could be compromised. We'll go through it in the order of the process that everything happens. So first of all, as I've already covered in a whole separate video, if this user account doesn't have pre-authentication enabled, we can just skip straight to step 2, get this user ticket and session key back from the domain controller, even though we don't have the user's password. At first glance, that doesn't seem like it would be of any use, but the session key part that is sent along with the ticket, the session key that's encrypted with the user's password, isn't just a session key. I simplified it slightly for the diagram. There's actually a whole structure that is encrypted with the user's password, the session key being one of the things in that structure. The reason I've not included the rest of them is because they're not very interesting. There's things like the domain name and the last time that a ticket was requested for this user, things like that aren't particularly interesting. But because this is a structure and certain parts of the structure will always have the same value, we can take that whole structure that's encrypted and just throw a load of different passwords at it with something like hashcat. So a program like hashcat is going to just loop through a list of common passwords, thousands and thousands of passwords, or just brute force single characters at a time. It'll loop through all those passwords, try to use those as the password to decrypt this whole structure, and when it sees certain values in certain positions, it knows that that's what the structure should look like, and then you've got the user's password. So that's the first attack, is if pre-authentication is not enabled, we can just get some data back straight away that is encrypted using the user's password. We can crack that offline, unless they have a really long, complex password. If we carry on, the second place that we can see an issue is that the TGT, the user ticket, is encrypted using the KRB TGT account password. If somebody manages to get the password for that account, well then they can just pretend to be anyone they want. Because now they can skip step 1 and 2, create their own fake ticket using that password to encrypt it, make up a random session key, put that inside the ticket and use that to encrypt the extra data, or the authenticator as it's called, and send that as a request to the domain controller. The domain controller is going to think that that's completely legitimate and that this user is whoever they say they are and that they are a member of domain admins or whatever you've put in the ticket, and it will send back a valid service ticket for any service in the domain that they can then use to do step 5 and 6 completely legitimately. And now when we get to step 6, the service is going to think that they are the domain admin. Now obviously it's not easy to get the KRB TGT account password, so that's not such a big worry. I've done a previous video that shows one way you can do that with a DC sync attack, but again, you need to have compromised some high-level accounts for that to happen, really. So that's not going to be a particularly common one, but it is a vulnerability, and that's what's known as a Kerberos golden ticket attack. If you hear that phrase, that is what they're referring to. It means that somebody's got the KRB TGT account password, and now they're creating themselves these golden tickets. They're called golden tickets because, as we've seen, you can use them to request tickets for any service on any machine on the domain, and also you can set the expiry date to be like 10 years. So it won't need to be renewed, it will just keep working forever. Until somebody changes the password for the KRB TGT account, which a lot of places never ever do. The next potential problem is with step 3 and 4, in that any user can request a service ticket for any service, regardless of if they should actually have permission to access that service. So if we've just got some bog standard domain user credentials, they're not in any admin groups or anything like that, we can go and request a service ticket for the SQL service. We'll then get back a ticket that is encrypted with that service account's password. And we can use the same technique with something like Hashcat to try and crack that offline. Again, based on the fact that the ticket is in a certain format, so we can keep trying different passwords as the decryption key, and when we get the right one, we'll know because we'll see a certain value in a certain position in that structure, and then we know we've got that service account's password. This is a technique called Kerberosing. I've done a separate video explaining that in detail and giving a demonstration of that. So I'm not going to go into that too much here, but you can hopefully see where that fits in. Which leads nicely into a silver ticket attack, which, as you can guess, is pretty similar to a golden ticket, except it only works for one service. So let's say we've done the Kerberosing technique to get the service account password for the SQL service. Well, now we can go straight to step 5. We can just create our own ticket, because if you remember in step 5, where we're authenticating with the service, the KRB TGT password and everything like that doesn't come into it here. We're assuming that that's all already taken place, but if we actually have the password for the SQL service, we can just create a fake ticket and again create a fake session key, encrypt the authenticator with that same session key, put that session key inside the ticket, which we can encrypt because we've got the password for this service account, send the whole thing to the SQL server, and it's going to treat it as being completely legitimate, which means we could just also put in the ticket that we are the domain administrator, and it will believe that and treat us as the domain admin, let us into all of the SQL databases that the domain admin should be able to access. So the defense against that whole thing is to just have really long, complex passwords for your service accounts. Don't give any service accounts simple, short, common passwords if they're going to be using Kerberos authentication. I mean, don't do that in general, but especially with Kerberos, because now anyone with basic user credentials can get some data encrypted with that password and try and brute force crack it offline. So you'll be pleased to hear that pretty much covers it for attack vectors, at least ones that I know of. I'm sure there are others as well. And like I say, if you want to see those attacks in action, I've done separate videos covering those already. And just to clarify something here before we move on, in this example where we're requesting a service ticket for the SQL service, we've created a separate user account in Active Directory to run that service, and that's what we've associated the SPN with, the service principal name. But what about network services that are just built into the operating system that just run as local system? So like when we access an SMB share on a machine, that supports Kerberos authentication. Remote PowerShell sessions support Kerberos authentication. There's plenty of services that are built into Windows on each machine that will allow you to authenticate with Kerberos, but that we don't set to run as a separate user account that we create in Active Directory. So where does the service principal name exist for those? How does the domain controller know which password to use to encrypt their service tickets? Well, it's pretty simple. It'll be the computer account that has the service principal name associated with it. And this gets done automatically. There's a special service principal name called host, which kind of encompasses a lot of built-in Windows services. Again, all the ones we mentioned like SMB, WinRM, remote registry, all these things. There's lots and lots of services. You can look up what's in that list. But basically, each computer account in Active Directory will automatically have this host service principal name associated with it. So when something connects to, say, an SMB share and wants to use Kerberos authentication, the domain controller is going to look for an account that has that host entry. It will find the computer account that has that service principal name. because again, the service principal name is the service followed by the machine name. So if we're connecting to a server called server 2, it'll be looking for a service principal name of host/server 2. It will find that computer account and it will use the computer account's password to encrypt the service ticket. Now, computer account passwords are very long and complex, and they're changed automatically every 30 days by the system. So we're not going to be able to brute force or crack those offline like we can with actual user accounts that are set to run services and support Kerberos. And there is a special user account you can use that behaves like a computer account. It's called an MSA, or a managed service account. And you can use that to run services, but it will have its password changed automatically every 30 days by the system, like a computer account. So that's kind of one solution to these attacks. Anyway, we got a bit sidetracked there. Let's get back to what we were talking about. So let's take a look at the actual messages that get sent across the network and what's contained within each of them. And like I said at the start, we'll do a live demo in a second showing how all of this actually looks in Wireshark. So to start with, when we're sending the request to the domain controller for a ticket, we have what's called an AS rec, or an AS request. When the domain controller sends back a ticket and a session key, that is an AS rep. So rec REQ being request, and then rep REP being response. Then when we want to request a service ticket, we have a TGS rec, TGS being ticket granting service, and then rec again for request. And we get back the service ticket and the session key for that in a TGS response. Once the user's got the service ticket, it sends it to the SQL server in an AP request. So let's look at what's contained in each of those messages. We'll go through it in order. First of all, we've got the AS rec. As we said at the start, this contains the pre-authentication data, assuming pre-auth is enabled for the user account. So that's going to be the current time encrypted with the user's password. It'll contain the username that we're requesting a ticket for, and kind of strangely, that will also contain the service name, even though it will always just be KRB TGT, because we're requesting an initial ticket. And as we know, that ticket will be encrypted with the KRB TGT account password. So the domain controller receives that, and it sends back the AS rep, which is the user ticket, or the TGT, and the session key. So let's look at what's actually inside this ticket, because we keep talking about tickets all over the place. What does it actually look like? Now, this isn't absolutely everything that's in a ticket. I've just picked out the interesting parts. So we have the name of the service that this ticket is for. In this case, again, because this is a TGT, an initial logon ticket, then this service will always be KRB TGT. Again, that seems really redundant, but it actually makes sense in the ticket because this exact same ticket format and structure is used for the service tickets as well. And for those, it is important to have the service name in there. But yeah, again, for this initial AS request and AS response, the service name isn't going to come into it really because it's always going to be KRB TGT. We have the expiry date. By default, that will be 10 hours. You can set the limit. Let me show you quickly on the domain controller. If we open up the group policy management console, it's already in there. If we open that up, we look at the default domain policy. This is where this will be set normally. Just go to settings to get a summary of it. You'll see we've got Kerberos policy here. And you can see here maximum lifetime for a service ticket and maximum lifetime for a user ticket. And they're both actually set to the same value, but one is in minutes and one is in hours for some reason. But yeah, they're both set to 10 hours. So that is the default lifetime for a user ticket or a TGT, and then for a service ticket, which is sent in the TGS request and response. But yeah, coming back to the ticket itself, the expiry date and everything else that you see in here other than the service name is encrypted with the KRB TGT account's password. So all of this stuff here is kind of secure and in theory can't be changed or forged. Again, if you get the password to that account, then you can easily forge the ticket, but in theory, no one can forge this. So the expiry date is secure. The authorization data, also known as the PAC, is something that Microsoft added to the Kerberos spec when they implemented it. Well, the authorization data is a feature of the Kerberos spec, but the actual format and this whole PAC structure is a Microsoft thing. So this is kind of the important bit that we want to be able to fake when we're creating a fake ticket, because this is what tells a service who this user account is, basically. It tells you their security ID and their group membership list. And those are the things that a service is going to use to decide if a user is allowed in. So that's definitely a very important part of the ticket. And then we've got the session key, which as we've discussed is the same as the session key that's sent alongside the ticket, but just will be encrypted with a different password. So in the ticket, it'll be encrypted with the service account's password. In this case, that service is KRB TGT because this is a user ticket or a TGT. And then you can see on the left-hand side that that same session key is in the AS response, but encrypted with the user's password so that they can get it if they've got the correct password. So now let's move on to step 3, which is where we've already got a TGT and we use that to request a service ticket from the domain controller. So we do that with a TGS request, and that contains the name of the service that we are requesting a ticket for. So this is where the service principal name will get constructed and placed in there. And then when the DC receives that, it can search Active Directory for the account that has that service principal name. Also in the TGS request is the ticket that we got from the initial logon process, so from the ASREC and the ASREP. And again, this ticket here is encrypted with the KRB TGT account, so we can't modify that or anything. We're just passing it on as part of the pre-auth data for this TGS request to prove that we have already logged on as that user account. And again, to prove that the ticket is authentic, we're also sending this authenticator, which is encrypted using the session key that is inside the TGT, and that was also sent with the TGT in the AS response message in the previous step. If you're not following that part, then just take another look at the AS response message, the AS rep, what that has inside it, and how the session key is included in that, and also in the ticket that is included in the message as well. So the domain controller receives this TGS rec, it sends back a service ticket and a session key. Again, the ticket format is exactly the same as it was for the TGT ticket, so this time the service name is actually important. And again, the rest of the data other than the service name is encrypted with the password of the service account. So not the KRB TGT account this time, but the account that's running the service, the account that has the SPN for this service in Active Directory. And again, the ticket contains an expiry date, which is set by that service lifetime policy we looked at earlier, and also the pack, so the list of all the groups that the user is a member of, which is copied directly from the TGT that was sent in the TGS request. So that pretty much covers the TGS exchange. So now we're on to step 5, which is actually sending the request to the SQL server. Now here we include the service ticket that we got back in step 4 in the TGS response. And again, this includes the session key, which we also use to encrypt the authenticator, which proves that we have knowledge of the session key, and therefore proves that this is a legitimate ticket. And this will literally be the exact same ticket that we received in the TGS response, just forwarded on as part of this message. So that's all of the theory out of the way. Let's take a look at how this looks in practice. To help demonstrate this, I've written an extremely simple program that just uses the built-in negotiate stream class in the .NET framework, which basically will negotiate whether to use Kerberos or NTLM. So we're going to run this on my machine and also run it on the server. This half of the code is when it's run on the server because we'll use /s, and this half is the client. Again, it's super simple and it's not in any way meant to be a good demonstration of coding or anything. There's loads of hard-coded passwords and stuff. This is not a good program. This is just purely for demonstration. But just to run through it real quick, on the server side, we're going to start a TCP listener on any IP address on port 4646, just a random port I decided on. We'll wait for a client to connect. When the client connects, we use this negotiate stream class that I mentioned, and that has a function in it called authenticator server. And we'll just let that do all the work for us. Basically, that will handle the Kerberos authentication. Once it's completed the authentication, we'll just print out the user's name, their groups that they're a member of, and also the authentication type that got used. So that should say Kerberos if we do everything correctly. Otherwise, it'll fall back to NTLM. We'll see NTLM in there. And then on the client side, we're just using TCP client to connect to the remote server. We are specifying some credentials here. Now, normally in Windows, you're not going to need to specify credentials to use Kerberos. That's one of the good things about it, is that when a user connects to a network service, it doesn't prompt them for any credentials. When the user first logs on and they get their TGT, that will get cached. And then whenever they need to request a service ticket, it will just use that TGT from the cache. So they don't have to keep putting their password in to get a new TGT. In this case, though, I'm going to be running this from a non-domain machine. So we need to specify some credentials because we didn't do that initial log on to get a cached ticket. This second parameter here for the authenticator's client function is the service principal name, which we've talked a lot about. So here I'm just going to pass that in the command line arguments. You'll see what I enter for that when we run the program. So I've copied the program over to this machine. Now this is the domain controller as well, but just pretend this is the separate SQL server. This doesn't have to be on the domain controller. It's just that I've only got the one VM here. So we're going to try and simulate the SQL service accepting the authentication by running this program as our SQL service account. So we'll just do run as user SQL SVC, start new command prompt. Except we can't because they can't log on to the PC or the server, sorry. There we go. Now they can. Cool, so we've got this command prompt running as that SQL service account, and we need to be running as that because that's the account that has the SPN associated with it. So we'll do this kerbdemo/s because that was how we set it up. And then on our client machine, we'll run kerbdemo, specify the machine that we want to connect to. Now you remember that I said you can't use Kerberos to connect to an IP address normally. That's because it's the service principal name that matters, and normally the service principal name will get constructed from whatever address you're trying to connect to. I've written that program slightly differently, so that's not the case. But yeah, ordinarily with most tools, if you tried to connect to an IP address, it's not going to use Kerberos. But as long as we specify the service principal name manually here in the correct way, we should be fine. So it was ms sql svc / and then the machine name, which was that. So if we do that correctly, you see we successfully authenticated using Kerberos. So now if we go back onto the domain controller, we will see that the authentication type was Kerberos. It thinks we're running as that JSmith account because that's the username and password we entered. And it can see that we're a member of all these groups. And they are the correct groups that that JSmith account is a member of. And again, that's because here we're specifying the credentials of JSmith. So let's look at that with Wireshark running. So we'll start a capture, and then we will do that connection again. It's connected, so let's stop the Wireshark capture, and we'll filter it to Kerberos. And now we can see the whole process and kind of tie that into all the things that we've been talking about. So we can kind of ignore these first two because that's just because pre-authentication is enabled on this account, which is the default. So if pre-authentication wasn't enabled, we wouldn't see this error message, but because it is, we get that error, and then it tries again with pre-authentication. So here we'll see the ASREC, which you remember from the diagram, hopefully. So this is the first part where we are requesting a TGT or a user ticket for this user account. And we can see that we've got this PA data, pre-authentication data, which is a timestamp, an encrypted timestamp. So that matches up nicely to everything else that we've seen already. We can also see we get the username in this client name or CNAME string. So that's the JSmith account. And then we get the service name, which will be KRB TGT, HTTP.local. So this is where the service principal name goes, basically. You'll see when we do the actual TGS request, that'll make a bit more sense. But for now, you can just see that the service name or S name is KRB TGT, as we showed in the diagram. So then we get to step 2 on our diagram, where the server sends back the ticket for the user in the ASREP message. So let's have a look at that. Again, we can see that the username that this ticket is for is JSmith. And then we get the actual ticket. So this is the ticket structure that we looked at. It has the service name in plain text. Anyone can read this. And then it has the encrypted part, which is all of those things like the expiry date and the pack. All of the group list and everything is in there. So that's all encrypted, so we can't just read that in Wireshark. Then we've got the second encrypted part, which is not part of the ticket. So this is where the session key goes that's encrypted with the user's password. So again, in the ticket here, in the encrypted part of the ticket, there will be that session key encrypted with the KRB TGT account password. And then in the encrypted part here, it's just part of the ASREP message. This will be encrypted with the user's password, and this also has a copy of that session key in. So that matches up with everything that we've seen so far. Then we get on to the TGS request, which is the user using that ticket to actually request a service ticket. So the original ticket, the user's ticket, the TGT, is in here. If we go into pre-authentication data, and then PA data TGS request, and then we get an AP request. So you might notice that that's actually the same type of message that we use at the very end of this to actually authenticate with the SQL service, an AP request. And that's just because we're doing the exact same thing here when you think about it. We're using a ticket to authenticate with a Kerberos service. And that's exactly what we do when we connect to the SQL server. It's also exactly what we do at this point. We use our user ticket, our TGT, to authenticate with the Kerberos service. In this case, that service happens to be part of the whole Kerberos system, which is the TGS, the ticket granting service. So we send it the ticket that we got, encrypted with the KRB TGT account password. So this is the exact same ticket that we got back in the AS response. And then we also send it the authenticator, which, like we said, is a load of data that's encrypted with the session key that is also present in the ticket that we got back in the AS response. Hopefully I've already done a good enough job of explaining that, but they can kind of see it in action. Then the main part of the request here is just requesting that we actually get a service ticket for a specific service. So this is where the service principal name comes in. Again, the service principal name that we specified, you see here, was this, MSSQL/DC1, blah, blah, blah. And that's what we have here. It's split into different parts based on where the slashes are, basically. Like you can have another slash here with another identifier at the end, and that will just get split into a third part here. But this is essentially the service principal name being sent across the network. So that's how, when the DC receives this request, it knows which account to go and look for to get the password from. So it does that, it goes and gets the password from that account, and then it sends back this TGS response, and then the service ticket itself. So this time we don't see KRB TGT in this, we see the MS SQL service, because that's the service that this ticket is for. This is no longer a TGT, this is a service ticket, this part. And then again, it's got the session key and all the pack and everything encrypted in here with the service account's password. So whichever account has this service principal name associated with it, this whole encrypted part is encrypted with that password. And then we also get a copy of the session key and some other data encrypted with the user's password here so that we can retrieve that. And then we send all that to the service. Now you might wonder why you're not seeing that last part where we actually send the AP request, and that's because up until now this has all been happening over the Kerberos protocol, whereas at this point when we start to actually send the authentication request to the server itself, the application server, so SQL in this case, now that needs to be done over whatever protocol it is that SQL server expects incoming data to come in. So it will be some proprietary SQL server protocol. In our case, because we're using this .NET program that just uses the built-in negotiate stream class, it'll be some proprietary protocol that uses. So we take the Kerberos filter off, and now we look for wherever the TGS rep is. So that was the last message that we could see. We'll now see some more messages being sent that are just general data. And if we look through them, if we actually keep an eye on the data down here, pretty sure we will see one somewhere. Yeah, so here we can see we've got http.local, MSSQL service, blah, blah, blah. So this will probably be part of the proprietary protocol or whatever that is sending the data over. Now I'm making some assumptions there. Okay, I don't know exactly what format the negotiate stream class sends its data in, but hopefully you get the idea that the final part, the AP request, step 5 in our diagrams, that gets sent kind of inside whatever protocol it is that the two programs are communicating with. So that might be HTTP, HTTPS, it might be something completely proprietary like this is probably using, or it could be the SQL server network protocol. Whatever it is, that will contain the actual Kerberos AP request, which will then get kind of stripped out of it and processed by the operating system as a Kerberos AP request. So I think that pretty much covers it. That was a very long video. I've got a sore throat now from talking so much, but I hope it explained some things to you. Sorry if I made things more confusing in some parts than they needed to be. Hopefully if you look at the diagrams enough, even with my waffling over the top of them, you can still get a good idea of what's going on. I will also post some static images of each of those parts of the process and all of the protocol messages and stuff like that. I will post those on my blog, which I'll leave a link to in the description so that you can go and have a look at those without having to watch this 10-hour video again to find the bits you want. And with that, I will leave you in peace, and I'll see you in the next video.